Dear students, let us start with part 4, and in this lesson we shall study the numerical problems on runoff, yield and MFD calculations. So before starting with problem 1, all of you should have at least a few pages, blank pages along with a calculator, so that whenever we will go through some calculation work, you should also do it and try to tally the results that we are getting here in this presentation. So problem number 1, the chronological record of the annual rainfall for a rain gauge station is given below. Find average annual rainfall at this station by arithmetic mean method. So in this problem, the rainfall data is given. So if you look at this data, you will find that for number of years, the rainfall data, that is precipitation measured in centimeter, is given. And if we look at the first one, and that is for 1938, and the last one, that is for 1972. So if we count the number of years, we will find that the rainfall data for a period of about 35 years is given here. So let us see, if we want to find out the average annual rainfall by arithmetic mean method, what is the procedure? So the formula which is used is very simple. In this, we have to find out the summation of the rainfall values, and we have to divide it with the total number of years for which the data has been given. So here this step is mentioned here, where we find the sum of all the rainfall values in centimeter from first year to 35th year, and as such here we get this total as equal to 5259 centimeters, and that is divided by 35, and as such we get the average value, that is 150.30 centimeters. Now in this, the catchment area is not taken into consideration, and that is why whatever result we get by arithmetic mean method, it is not so reliable. So let us see second problem. In following table, catchment area with average annual rainfall data of rain gauge station is shown. Find out the average annual rainfall by Thyssen polygon method. We have already learned the theory of Thyssen polygon method in a given diagram, where the different rain gauge stations are shown, are joined together, it is bisected and that results in formation of polygons. So the area enclosed into each polygon is measured with the help of planimeter, and for each rain gauge station we also have the value of rainfall. So as such, here the first column is related with the rain gauge stations, the second column here is related with the area measured in square kilometer, and the third column is precipitation, that is rainfall measured in centimeters. So in this data, although we find number 1 to number 8, but here at 5 number we don't have any data, so we can just ignore it, and as such for this given data we can find out the value of average annual rainfall. So let us see the procedure. So here we can see that the formula which is used includes the multiplication of precipitation and the area enclosed in that catchment. So as such, for number of rain gauge stations, we are having 7 stations. So for 7 stations we have the values of precipitation as well as the area correspondingly responsible for that particular rain gauge station. So as such, in this particular step we find that the multiplication of the precipitation and area is done for all the given data, and that is divided by the summation of the area of the catchment enclosed into that number of polygons. So finally, when we do all the calculations, we get the total that is equal to 10940, and that is divided by the total of the area, that is 82.50 square kilometer. And as such, when we find the result, we will get it as 132.60 centimeters. So thus, by Thyssen polygon method, we get the result of average annual rainfall is equal to 132.60. So here, as we see that the area is also taken into consideration, and that is why this particular method will give us more accurate result. Now let us go to problem number 3. Using the following data, find out the average rainfall by isohydral method. So isohydral method also we have learned in the theory in previous lesson. So in which, for a given map, the isohyds are shown enclosing the different rain gauge stations. With the help of planimeter, the area enclosed between the two corresponding isohydral lines is measured. That gives us the enclosed area between successive isohyds, and also we have the value of precipitation. Now here, for example, for isohyd having a value 105 and the isohyd having the value 110, if we consider the area enclosed between these two isohyds is measured as 1 kilometer square. Now this is the area, and what about the precipitation? So precipitation, value of precipitation can be obtained as a mean value. So 105 plus 110 divided by 2, that will give us the mean value of precipitation, that is 107.5. In the similar way, we can find out the value of the precipitation, mean value of precipitation and area for all the data that is given in this particular table. Now let us see the calculations. The similar formula that we have used in previous case is observed here. That is, here also we find that for each set of data we will do the multiplication of precipitation and area, and we will carry out it for all the given data, and that is divided by the total of the area. So here in this step, this calculation is shown. All the values have been placed in the formula, and after calculation we get that the total is equal to 10396 divided by the total of the area, that is 78.50 square kilometer. And when we solve this, what we get? We get the average value of annual rainfall, and that is 132.40 centimeters. So in this method, isohydral method also, we take into account the areas, and therefore this method also gives us the reliable result. Now let us go through problem number 4. Catchment area of a large proposed reservoir is given as 9362, that is 9362 square kilometer. Calculate 75% dependable yield. Use the rainfall data given below. So again here we see the similar rainfall data for 35 number of years, and here we have to calculate the yield, but it is the dependable yield. And what is the percentage of dependability? That is 75%. So the catchment area is given. If it is multiplied by runoff, we will get yield. But for runoff, we must have the rainfall value, and that rainfall value must be corresponding to 75% dependability. So therefore, we have to follow a particular procedure so as to obtain all these steps. So let us go through the different steps. So here yield is given by the formula catchment area into runoff. So as our discussion, we must have the rainfall value corresponding to 75% dependability. So for that, a particular procedure is to be followed. And what is that procedure? Whatever data of rainfall was given in a chronological manner with respect to the year, so that is to be written here again in a descending order. Descending order in the sense, the greatest value of the precipitation is to be written first, and then below it the lower values. As such, at the end we will find the lowest value of the rainfall written. After writing all these things, we have to write down the serial number for these data arranged in a descending order. Now, what is the next step? So therefore here a formula is used to find out the serial number corresponding to 75% dependability. So serial number is equal to dependability percentage into n. So percentage dependability percentage is 75%. So here we will put the value of 75%, and the number of years is 35. So 75% into 35, we get this result as equal to 26.25. So for a serial number 26.25, whatever rainfall is given in this table will be the required value of rainfall to be used for the yield calculation or runoff calculation. Now how to find out? Because this is not a integer value, so therefore if you look at the table, we are having the serial number 26 and the serial number 27. So at serial number 26, we are having the rainfall value is equal to 131, and for serial number 27 it is 126. Now how to obtain the rainfall corresponding to 26.25? So for that, actually roughly if we want to do the calculations, we can take just the mean of these two, that is 131 plus 126 divided by 2, but that will not give us the accurate value. So therefore to calculate the exact value, what we should do? We should follow the interpolation method. So this interpolation method we have already studied in surveying. So the same method we have to apply here. So in that, what is to be done? For serial number 26 and 27, we will find out the difference between these two serial numbers, and that is equal to 1. Similarly, the corresponding values of precipitation 131 and 126, we will find out the difference between these two, that is 126 and 131, and that is equal to 5. So similarly, we will find out the difference between the required value of serial number, that is 26.25, and the first serial number, that is 26. So that and this difference we get here as equal to 0.25. Now we have to find out whether there is an increment or decrement in this value. So by interpolation method, we can use a simple step, that is equal to 0.25 into 5 divided by 1, that is equal to 1.25. So we have to either add this or decrease it. So that is increment or decrement. So how to decide it? So if we look at the values at serial number 26, it is 131. At 27, it is 126. This means the values are decreasing. So it is a decrease. It is a decrement, and therefore the required rainfall is equal to 131 minus 1.25, and that is equal to 129.75. So this value of the rainfall 129.75 centimeter correspond to 75% dependability. So this is to be used for runoff calculations. So we shall see these steps in the next slide. So here let us calculate now runoff. So we can calculate the runoff by the three methods: English method, Binnis percentage method, and Strange's percentage method, and whatever is suitable value that we will choose for the yield calculation. Now by English method, we know that there are two formulas for ghat area and non-ghat area. The value of precipitation that we have considered is 129.75, which is less than 200, and therefore we have to use the English formula for non-ghat catchment area. So the formula is R is equal to P into bracket P minus 17.78 divided by 254. So let us put all the value of precipitation here and solve it. So when we solve it, we get the result of runoff is equal to 57.19 centimeter. Now let us calculate it by the second method, that is Binnis percentage table. So we have already seen in the previous lessons the Binnis percentage table. So if you remember that table, actually it should be in front of you now. So please take out your notes in which the Binnis percentage table is given. So this is a table of Binnis percentage versus the Binnis percentage of runoff versus the rainfall. Now what is the value of rainfall that we have considered? 129.75. So in that table, if we search for this value, we get the value that is 127.5 first rainfall value, and second rainfall value is 130 centimeter. So we do not get the exact value of 129.75, but we get the value in between 127.5 and 130. So again, what we have to do, we have to follow the interpolation method and find out the required value. So from the Binnis percentage table, for a rainfall of 127.5, we get the runoff percentage is equal to 45%, and for 130 centimeter rainfall value, the runoff percentage is 45.6%. So with this data, if we follow the interpolation method, we get the value of the runoff percentage as equal to 45.54. It is given here 45.54%. So therefore whatever value we have chosen of rainfall 129.75 multiplied by 45.54%, this will give us the result of runoff, and we get here the value of runoff is equal to 59.08 centimeter. So this value is a little higher than the previous result that we have obtained by English method. Now let us see the procedure for the Strange's percentage table. Now remember the Strange's percentage table, keep it in front of you, that we have already seen in the previous lesson. Now for the value of rainfall 129.75, we will search this value. But if we look at this table, Strange's table, in that the average annual rainfall is not given, but the monsoon rainfall is given. So therefore it means that we have to first calculate the monsoon rainfall. So therefore, see, this monsoon rainfall is assumed to be 95% of the average annual rainfall. So therefore what we have to do, 129.75 multiplied by 95%, and that we get as equal to 123.26 centimeters. So for this value of rainfall, we have to find out the straightage percentage. So again look at the straightage table. So we will not get this exact value of 123.26. So what we are getting? We are getting the value of 122.5, and we are also getting the value of 125 centimeter. So our value is in between these two values, and therefore what we have to do? We have to follow the interpolation method. So by interpolation method we can calculate the required straightage percentage. So by interpolation method, so this you can do in rough, as we have already seen in the previous case. The similar procedure you have to adopt and find out what is the straightage percentage by interpolation method. So if we calculate this interpolation method, adopt this interpolation method, we get the value as equal to 47.96%. So runoff can be calculated from here. So 123.26 rainfall value multiplied by straightage percentage 47.96, that will give us the runoff value, and that is equal to 59.11 centimeter. This is still a little higher than the previous value. As such, here by adopting these three methods, we are having three set of the runoff value. Now what is the next step? The next step is to calculate the yield. Out of these three, which value of runoff is to be adopted? So we have to assume the minimum value of the runoff, and that is by English method, and 57.19 centimeter. So let us put it in the formula: yield is equal to catchment area into runoff. So catchment area we have already seen in the given problem, 9362 square kilometer, that is to be converted into square meter, and for that you have to multiply it by 10 to the power 6, multiplied by the runoff value, it is in centimeter, convert it in meter, that is 57.19 divided by 100, and when we complete this calculation we will get the result. So we get a big figure, that is 5354127,800 cubic meters. So let us convert it into million cubic meter, and for that it is to be divided by again 10 to the power 6, and as such finally we get the result 5354, that is 5354.12 million cubic meter. Now this is the answer for 75%, answer of 75% dependable yield calculated for the proposed data. Now whatever value of the straightage table we have, from the straightage table we have chosen, again there we will find the three bifurcation of the rainfall value for good catchment area, bad catchment area, and average catchment area. So in this problem, because the type of catchment is not given, so we have to assume it as a good catchment area and therefore we have chosen the value of good catchment area accordingly. Now let us go to the next problem. Problem number 5. A reservoir has catchment area of 1200 square kilometer, and another reservoir within this catchment area has area of 800 square kilometer. Average annual rainfall of the catchment area is 120 centimeter. The runoff of an average bad year is 22% of the rainfall of an average bad year. The runoff from the intercepted catchment area is 20% of actual runoff. Calculate the total assured yield. So in this problem we have to calculate the total assured yield, the total yield we have to calculate. So here it means that there are two catchment areas. One is intercepted catchment area and other is independent catchment area. The total catchment area is 1200 square kilometer. From that you have to find out the intercepted and the independent catchment area values. So total yield will be equal to the yield from the independent catchment area plus yield from intercepted catchment area. So I have to find out these two values separately. So what is the intercepted catchment area? That is directly given as 800 square kilometer. Now what is independent catchment area? That can be obtained by deducting intercepted catchment area, that is 800, from the total catchment area, that is 1200 square kilometer. As such we get the independent catchment area as equal to 400 square kilometer. Now what is the next step? Now here one term is used, that is the rainfall of the bad year. Now this is a new term. So what is this? A bad year is one in which the rainfall is less than 80% of the average annual rainfall. So it means that whatever value of the average annual rainfall is given in the problem, that is 120 centimeters, we cannot take it directly. We have to first find out the rainfall value for bad year. So that can be obtained here by a simple step, by multiplying 120 with 80%. So 80% into 120, that is 96 centimeter. So 96 centimeter is the rainfall value for the bad year, and that we have to consider to calculate the runoff. So now we will calculate the runoff from two different areas. So first, runoff from independent catchment area. So in the problem itself it is given that the runoff of an average bad year is 22% of the runoff of the average bad year. So what does it mean? So runoff from independent catchment area. So this will be the runoff from independent catchment area, and that can be calculated directly. So 22% into 96, that will give us the runoff from independent catchment area. Once we get this value, we can find out the second value, that is runoff from intercepted catchment area. Now again it is given in the problem, the runoff from the intercepted catchment area is 20% of the actual runoff. Now here the actual runoff will be 21.12 centimeter, that we have already calculated. So what we will do, 20% into 21.12, so we get here the value of 4.22 centimeter. So as such we have obtained two different runoff values. Now with this, if we can continue to calculate the yield. So first we will calculate the yield for the independent catchment area. The independent catchment area is 400 square kilometer. So that is multiplied by runoff from independent catchment area. So 400 into, now this is 400 is square kilometer, that is to be converted into square meter. So 400 into 10 to the power 6, and that is multiplied by runoff. It is 21.12 centimeter. You convert it into meter, that is 0.21, and if you do this calculation we will get a figure, a big figure, 84.48 into 10 to the power 6 cubic meters. So again we have to convert into required unit of million cubic meter by dividing this value with 10 to the power 6, and therefore we get the value as equal to 84.48 million cubic meters. Similarly we will calculate the value of yield from the intercepted catchment area, and intercepted catchment area is 800 square kilometer multiplied by 10 to the power 6 multiplied by 4 centimeter, that is 0.04 meter, and thus we get here the answer is equal to 33.76 times 10 to the power 6 cubic meters. So convert it into million cubic meter, that is 33.76 million cubic meter. We have obtained these two values. Now what we have to do? We have to do just the summation of these two. So the total yield is equal to 84.48 plus 33.76, and as such finally we get the answer is equal to 118.24 million cubic meter. So dear students, whatever calculations I am explaining here, please do it roughly, and for doing so you can pause this video whenever it is required. Now let us go to the next problem. Problem number 6. Calculate MFD, that is maximum flood discharge, from 500 square kilometer catchment area using English and Dickens formula. So for Dickens formula, the value of C constant is given 14.5. So first of all, by using English formula, Q is equal to 123 times A divided by root of summation of A plus 10.24. This is a standard formula. In this, A is the catchment area and it is to be written as it is in square kilometer. It need not be converted into square meter. So if we put this value of 500 in this formula, we can solve it and we get a result is equal to 2722.63 cubic meter per second. MFD is discharge and therefore discharge unit will be there. So you can check this calculation. Now let us use the Dickens formula. Q is equal to C into A to the power 3 by 4. Put the value of 500, C is equal to 14.5, and when we solve this, we will get this value or result as equal to 1533.19 cubic meter per second. So like this, by using the Dickens and the English formula, we are having these two results. Now which value should be actually considered as a design value of MFD? Now in this problem there is no question of design value. We have to simply calculate the result by using these two formulas. However, in our answer we can write down the design value. If two such values are available of MFD, the higher value should always be considered as the design value. So at the end here, as usual, I have given you the question bank. Two questions are given for practice. So please solve these two questions in your assignment book. I hope you have prepared and you have solved all the assignment, all the questions that I have given in the previous parts, theory as well as numerical questions, and in this part 4 also solve these two questions. For more practice, you can refer to the model answer available on the MSBTE site, and as such you can solve the questions on this topic by searching into that model answer and have more practice. You can also refer to the available textbooks and you can solve the unsolved problems. So more you practice numerical, the concept will be more clear to you. So dear students, this is the end of unit 1, that was introduction to irrigation and hydrology. From next slide we shall start with study of unit number 2, that is crop water requirement and reservoir planning. So I hope you have understood the numerical problems explained in this slide, in this presentation. Please practice some more problems. Happy learning. Thank you.